Next topic is linear transformation. Let V and capital W be two vector spaces, and T is a function from V to W. T a function, then T is called a linear transformation, shortly denoted by L dot T dot, linear transformation. If these two conditions are satisfied, that is T V1 bar plus V2 bar is equal to T V1 bar plus T V2 bar, or T V1 plus V2 is equal to T V1 plus T V2, for all V1 and V2 belongs to capital V, that is domain of this function. And T of Kv is equal to KTV. If this is equal to, if T of Kv is equal to KTV, for all U belongs to, for all V belongs to V, for all V bar belongs to capital V, and for any scalar K. If these two properties are satisfied by this function T from vector space V to W, then we say a T is a linear transformation. Okay, so show that the function T from R3 to R square define as the, so the notation for the linear transformation is generally capital T, capital F, capital L, M. These are the notation, small f, small g. These are the notation for the linear transformation. So show that this function T from R3 to R2. This R3 is, we know that R3 and R2 are two vector spaces defined as T x y z is equal to x plus y comma x minus z. So this is the x y z is the element of R cube. Obviously, this is three tuple, and the x plus y comma x minus z is the element of R square. This is order pair. So this is the function from R3 to R2, and we have to show this function is a linear transformation. Similarly, the another two examples. So answer of first example. Now we have to show this first property T of V1 plus V2 is equal to T V1 plus T V2. So we will take first V1 and V2 as the element of this domain that is R cube. We take the two element of R cube. So V1 is equal to this is the answer of third. So this is T is from R square to R cube. R square to R cube defined as Txy is equal to x plus y comma x minus y comma 2x. Obviously this x order pair xy is the element of R square, and this x plus y comma x minus y comma 2x is the element of R cube. So we have to show the two properties for this example number 3, also for example 1 and 2. So we have to take the first two element of R2. So R2 is R square is the domain. So we will take two elements. Suppose V1 bar. So this R square, the element of R square are order pairs. So we will take two order pairs, x1 y1 and x2 y2. Suppose V1 bar and V2 bar, these are the element of R square. So in the place of V and W, there are any two spaces. Suppose V is the space of M2 by 2R. That is the vector space of all 2 by 2 matrices with real entries. Then we take V1 bar and V2 bar as two element of M2 by 2R. That is, we will take V1 and V2 as the 2 by 2 or 2 by 2 matrices. Okay. So like that, this is R, V is R cube. Then we take 3 tuple, 2 3 tuple. If this V is a suppose V is a P2, capital P2, that is the, or P2X, that is the vector space of all polynomial of degree less than or equal to 2, then we have to take V1 and V2 as two polynomials of degree 2. So we will take the two elements from this R square, that is V1 as x1 y1 and V2 as x2 y2 belongs to R square be any element. Then what is V1 plus V2? What is the addition in R square? That is the usual addition. X1 is again order pair, x1 in round bracket x1 plus x2 comma y1 plus y2. Then T of V1 plus V2 is equal to T of x1 plus x2 comma y1 plus y2. Don't write this bracket, write this bracket, x1 plus x2 comma y1 plus y2. And what is T of xy is x plus y comma x minus y comma 2x. So what is T of x1 plus x2 comma y1 plus y2 is the three tuple x1 plus x2 plus y1 plus y2, the addition of these two, x plus y comma x minus y, that is x1 plus x2 minus, write in bracket y1 plus y2 or minus y1 minus y2, this minus this, x minus y comma 2x, that is 2 into in bracket x1 plus x2, that is 2x1 2x2, and then complete round bracket here, complete round bracket. So this is C tuple. And now we have to show it is T of V1 plus V2. So in order to show T1, it is equal to T1, T of V1 plus V2 is equal to T1 plus T2. This is the adjustment. Or we can denote this equation up to this equation number 1, and then separately find T of U1, T of V1 plus T of V2 separately. T of V1 plus T of V2, and show the RHS of the equation number 1 and equation number 2 are same. Okay, or adjust here. So what is the adjustment? Now we write this x1 plus x2 plus y1 plus y2 as x1 plus x2 plus x2 plus y2. Then we write here x1 minus y1 plus x2 minus y2, and there write 2x1 2x2 as it is. Okay, and then we reuse the definition of addition of two vertex vectors in R3. That is, we write this is the addition of x1 plus x2 comma x1 minus y1 comma 2x1 plus x2 plus y2 comma x2 minus y2 comma 2x2. That is, the addition of these two is again this. Okay, so we reuse the definition of that, reversely use the definition of addition in R3. So as this, and this is T of x1 y1 by using definition. What is T of xy is x plus y, x minus y 2x. What is T of x1 y1 is x1 plus y1 comma x1 minus y1 comma 2x1. So this is the T x1 y1, and this is T x2 y2. Okay, so this is T v1, this is T v2, and therefore what we have, T v1 plus v2 is equal to T v1 plus T v2 for all v1 and v2 belongs to R. Or we can denote this equation as equation number 1, and then this is the find T of v1 plus v2 as this equation number 1, and then consider T v1 plus T v2 separately. What is T v1 plus T v2? v1 is x1 y1, v2 is this. Then write T of v1 x1 y1 as this, T of x2 y2 as this, and then add these two, we have this, and then after adjustment we have this. So we show LHS and RHS are same in another method. And the second property, we take V bar as xy belongs to R square and k be any scale. That is, we take the element of this R square, any element of R square, and k as any scalar. So suppose V as xy, or take V1 as x1 y1 belongs to R square. V as a xy, order pair xy belongs to R square, and k be any scalar. And then what is k V bar is kxy is kx comma ky. This is by using the definition of scalar multiplication in R square. And then what is T of kv is T of kx comma ky. What is kv? Kv is this kx ky. And then this is equal to, by using the definition of T, it is kx plus ky comma kx minus ky comma 2 of kx. And if you take k as common from all these, we have k in bracket x plus y, x minus y 2x, and this is T of xy. This x plus y comma x minus y 2x is T of xy, and that is xy is V bar. So k T V bar for all V belongs to R square and for any scalar k. And that is what we have, T k V bar is equal to k T V bar for all V bar belongs to R square and for any scalar k, because V bar is any vector of R square, and it is true for any vector, so it is true for all vector of R square, and hence T is a linear transformation. So in order to show the function is linear transformation, we have to show the two conditions. So similarly, we will solve this these two examples. T x y z is x plus y comma x minus z, and this is T from R3 to R3. T x y z. So the element of R3 as the 3 tuple x y z is equal to x plus y comma x plus z comma x minus y. And again, these remaining two are also linear transformation. In the same way, we will show that the remaining are two are the linear transformations. So determine whether the following examples determine whether the Txy is equal to x comma x plus y comma x plus 3. Is it linear transformation? Is linear transformation. So the answer of the first is not linear transformation because of this x plus 3. And if the when the function is not linear transformation, if out of these two conditions, one condition, at least one condition fails for that function. That is T of V1 plus V2 is not equal to T V1 plus T V2, or we have to show T of KV is not equal to K of TV. Okay, so one of them condition fails. That is, we will prove the condition in the condition out of the two condition fails by using counter example or by using general example. So see this answer of the first problem. We will give the answer in two ways. So let's take V1 as x1 y1, V2 as x2 y2 belongs to R square. We take two elements from R square, be any vector. Then V1 plus V2 is x1 plus x2 comma y1 plus y2, and then T of V1 plus V2 is what? T of x1 plus x2 comma y1 plus y2 by using definition. So what is the definition? T of xy is x comma x plus y. So T of x1 plus x2 is x1 plus x2 comma x1 plus x2 plus y1 plus y2, that is x plus y, comma x plus 3 means x1 plus x2 plus 3. So this is by using the definition. And this we can write this as x1 comma x1 plus y1 comma x1 plus 3 comma plus x2 comma x2 plus y2 comma x2 plus 3. We cannot write like this. We cannot write this as like this. So, and this is not T of x1 y1 and T of x2 y2, or we denote this is as equation number 1. This is equation number 1, and then find separately T of V1 plus T of V2. So what is T of V1? T of V1 is T of V1 is T of x1 y1. T of V2 is T of x2 y2. And what is T of x1 y1? Is x1 comma x1 plus y1 comma x1 plus 3 by using definition of this. And what is T of V2? That is T of x2 y2 is x2 comma x2 plus y2 comma x2 plus 3. And what is the addition of these two? Is x1 plus x2, x1 plus y1 plus x2 plus y2 comma x1 plus x2 plus 6. That is, it is not plus 3. So what is the addition of these two? Is x1 plus x2, x1 plus x2, x1 plus y1 plus x2 plus y2 comma x1 plus x2 plus 6. And that is equation 2. And then we say that T of V1 plus V2 is not equal to T of V1 plus T of V2, and therefore is not linear transformation. The T is not linear transformation. Or we can prove this property, that this property is not satisfied for this T by using counter example. That is, take two particular elements of this R2. This R2, that is suppose 2, 3, V1 bar as 2, 3, and V2 bar as 8, 1 belongs to R square B any vector. Then what is V1 plus V2 is 10, comma 4. Okay, addition. And then what is T of V1 V2 is T of 10, 4 is 10, and then 10 plus 4, that is 14, and then 10 plus 3, 30 by using this definition, x comma x plus y comma x plus 3. So we have this. And then what is T of V1 plus T of V2? T of 2, 3, V1 is 2, 3, and T of 8, 1, and it is what? 2, 2, then 2 plus 3, 5, and 2 plus 3 is 5 by using the definition. And then 8 plus 1, 9, and 8 plus 3 is 11. And what is the addition of these two is 10 plus 14 plus 16, not 10 plus, not plus, 10 comma 14 comma 16. And what is this is not equal to 10, 14, 13. It is 10, 14, 16. So T of V1 plus V2 is not equal to T of V1 plus T of V2. What is the, we have to write T of V1 plus V2 is not equal to write T of V1 here, right? T of V1 plus T of V2. And therefore T is not linear transformation. So we can prove that the condition 1 fails for this example number 1 in two ways, either by using this way or by using giving the counter example. But I think the counter example method is a powerful method, easy method. So similarly, the 5 number, example number 5 is again not linear transformation. So we will show that the second property fails for this 5. So how can show the second property fails by using counter example? So like V bar as 2, 3, 4. So here the T is from R3 to R3. So we have to take the one element from R3. Suppose V bar as 2, 3. What is the element? 2, 3, 4 is the element of V R3. And take K as a 2, scalar 2. And then what is K V bar is 2 into 2, 2 into 3, and 2 into 4 is this 4, 6, 8. And what is T of K V bar is T of 4, 6, 8. And T of 4, 6, 8 is 1, 1, 1. So this is the image T of xyz. Whatever may be xyz, T of xyz is 1, 1, 1. That is constant function. So T of this 4, 6, 8 is 1, 1, 1. And K T V bar is 2. K is 2. T V bar is 2, 3, 4. And what is T of 2, 3, 4 is again 1, 1, 1, because T of xyz is 1, 1, 1 for all xyz. And so, and after multiplying by 2, we have 2, 2, 2. And therefore, what is your observation? That TKV bar is not equal to KTV bar, because KTV bar is 2, 2, 2, 2. And TKV bar is 1, 1, 1. And therefore, these two are not equal, and therefore, T is not linear transformation. So in some examples, the condition 2 fails. In some example, condition number 1 fails. In some example, both conditions fail. So we have to write only one condition fails, that is the counter example for one out of the two condition, one condition out of the two conditions. So similar examples, T from R3 to R square as xyz is equal to x comma yz is again not linear transformation. These are all the this Txyz as x square zy. X square is the problem here, yz is the problem. So if you take x in the two element from R3, suppose first element is 2, 3, 4, and another element take as a minus 3, 4, 5. So it take in x as positive and x as negative, and then we will find that, and then we will show that Tx v1 plus v2 is not equal to T of v1 plus T of v2. Okay. So take x as positive and x as negative. So take two elements from R3 such that, for example, v1 as minus 2, 3, 4, and v2 as 3, 4, 5, 3, 4, 9, or any we will take. In one example, we will take x coordinate as positive and x coordinate as negative in another vector. So take two vectors, and then we will see that T of v1 plus v2 is not equal to T of v1 plus T of v2. Similarly, this is not linear transformation. We'll take the two element x y as some x and y are in one example v1 take v1 as 2, 3, and in another example we take minus 2, minus 3. That is we will take v1 as 2, minus 3, and v2 as minus 4, 3. That is, one of them is negative, and then we will see that the first property fails. Similarly, the second property fails for this. That is, if you take k as negative number, then we have T of xy, T of k v bar is not equal to kt v bar. So write the counter examples for the fail property. So similarly, this is the example. Let V be a vector space of continuous functions on closed interval 0, 1. Define a map T from V to R. So V is the vector space of functions, continuous functions on closed interval 0, 1, real and root functions. And the definition is T of f is integration 0 to 1 fx dx. Then show that T is a linear transformation. So we have to show first T of f plus g is equal to T of f plus T of g, because now the notation for the elements of this domain V are f, small g, small h. So take two elements from this V, and then what is T f plus g is integration 0 to 1. This is Tf. So what is T of f plus g, right? Just f by f plus, replace f by f plus g. So integration 0 to 1 f plus g x dx. And by using the definition of addition of two functions, f plus gx is fx plus gx. And by using the property of integration, we know that integration distribute over addition straightforward. So integration of u plus v is integration of u plus integration of v. So integration of fx plus gx dx is integration of fx plus integration of gx. And this is T of f, and this is T of g. So what we have, T of F plus G is equal to Tf plus Tg for all F and G belongs to V. Now F is the element of V and K be any scalar. Then what is T of Kf? So this is T of F. So just we have to write T of Kf. So replace F by Kf. So Kf x dx, and is by using the definition of function, it is K of Fx, and K is constant. So by using the rule of integration, we will take this K outside the integration. So we have K integration 0 to 1 Fx dx, and this is Tf. And so what we have, K is equal to K Tf, and therefore K Tkf is Ktf for all f belongs to V and for any scalar k, and therefore T is a linear transformation. So these are some examples of linear transformation. Now we will see some more examples of linear transformation in the next lecture.